Welcome to Brain Vision.
In this question, there are 5 forces acting on the car. The weight force, the normal force that is exerted by the ground because the car is on the ground. Then we have that downward force due to the wind, and that backwards force that is also due to the wind. Then there is the frictional force. Well, the frictional force is rather counterintuitive because usually we would think that if the car is going in this direction, then the frictional force would be in that direction. But this is not the case here. And why this is so? Well, it is very similar to how can we walk on the ground. So, what happens when we are walking is that here is the floor, and then we push the floor, and then the floor pushes us, allowing us to walk. So when you are walking in this direction, the floor is pushing you in that direction. So it's the floor that is pushing you. Then the frictional force pushes you in the same direction you are moving. It's a very similar thing that happens with a car. So the car is moving in this direction. Then its tires are rotating like that. So when it's rotating, if there was no frictional force, the car would be in place and the tires would be rotating and sliding on the floor. But thanks to the frictional forces, what happens when the tire tries to rotate is that there is a relative movement between the tires and the ground. And then the frictional force tries to seize that relative movement. And as a result, we can see what happens. This part of the tire tries to move in this direction. Then the frictional force opposes itself to that movement, pushing the tire in that direction. So, thanks to that way of work of the frictional force, the car is able to move. So what the car is doing all the way is pushing the ground backwards, and the ground is pushing the car frontwards. So this is why we have a frictional force that is pointing in the same direction as the velocity of the car. Now we can proceed to the question. So the question is, what is the highest possible acceleration such that the tires don't slip on the ground? To answer that question, we have to apply Newton's second law in this direction, in the vertical direction, which I will call the y direction, and the horizontal direction, which I will call the x direction. And notice that I had already chosen my reference frame. Everything that is pointing to the right is positive, everything that is pointing up is positive, everything that is pointing to the left is negative, and everything that is pointing downwards is negative too. Then, applying Newton's second law on the horizontal direction, we get the following. So, for the horizontal direction, Newton's second law tells us that the net force on that direction is equals to the mass of the car times the acceleration of the car in that direction. Then, what are the components, what forces are composing this net force? So, in the horizontal direction, we have 2 forces, the frictional forces and this resistant force. So, the frictional force minus that resistant force is equal to the mass of the car times the acceleration of that car. Okay, then we can calculate the acceleration of the car as follows. The acceleration of the car in the x direction is equal to the frictional force minus that 1190 force divided by the mass of the car, which is 690. Then, remember that the frictional force is given by the following expression. The frictional force is equal to the static frictional coefficient times the normal force. Again, the car is moving, but we use the static frictional coefficient. Why is that? This is because this point of the tire that is touching the ground isn't moving with respect to the ground. If it were moving, then the car would be slipping through the ground, and this is not what's happening. Therefore, we have to use the static frictional force, because this point of the tire, the point that is in contact with the ground, is at rest with respect to the ground. Then, the horizontal acceleration is equals to that static frictional coefficient 0.87 times the normal force minus 1190 divided by 690. Now we have to calculate what is the value of the normal force. For that, we apply Newton's second law on the y direction. It tells us that the net force on that direction is equal to the mass of the car times the acceleration in the vertical direction. Note that the car is at rest in that direction, so this is equal to 0. Therefore, the net force in the y direction is equal to 0. The forces that compose this net force are the normal force, the weight force, and that downward force provoked by the wind. Then, we have the following. The normal force minus this downward force minus the weight force is equal to 0. Then the normal force is equal to that downward force plus the weight force. Now, we have the following. The downward force is equal to 4060 newtons. Then, we have the weight force. The weight force is given by the following expression. The mass of the car times the acceleration of gravity. The mass of the car is 690. And remember, the acceleration of gravity is approximately 9.8 meters per second squared near the surface of the Earth. So we have this. Then, the normal force is equal to 10,822 newtons. So, the acceleration of the car in the x direction is equal to 0.87 times 10,822 minus 1190 divided by 690. And this gives us an acceleration of approximately 12 meters per second squared. And this is the maximum possible acceleration. Any acceleration above this value will make the tires of the car slip on the ground. And well, note that this expression for the static frictional force is useful when we are calculating the maximum possible frictional force. So, this means that we are using the maximum possible frictional force to calculate the acceleration.